Hey guys, Mr. Betts here. I want to go through a few examples where we are using a differential equation with an initial condition to find a particular solution. And we're going to do that using the process of separation of variables. Now, the differential equations that I'm using in these examples are the same ones that I did when we were finding general solutions. So I'm going to go through that part of the solution fairly quickly and spend a little more time talking about the particular solution part using the initial condition. So we're going to start here by separating variables. And then once we separate variables, we're going to take the antiderivative on both sides. So we get y squared equals x cubed plus 3, not 3c, sorry. And then what we're going to do is, at this point, we can use this initial condition to find c. When I was finding the general solution, at this point I solved for y, and I got a particular solution. I got a general solution that had the plus c involved in the expression in some way. Here I'm going to actually solve for c first, and then I'm going to solve for y. So I'm going to go over here to the side and plug 2 in for y, 1 in for x, and we end up getting c equals 3. So we have y squared equals x cubed plus 3. Then we're going to solve for y. So taking the square root of both sides, we get y equals positive or negative square root of x cubed plus 3. Now, the last thing I want to do here is I want to restrict the domain, and actually in this case also the range, based on the initial condition. If you remember, the solution curve can only be part of a continuous section. And so this right here actually has two branches. It has a top half and a bottom half. And this 1, 2 is actually only on the top half. And I know it's on the top half because the y value is positive, and so it has to be the positive here. So I'm going to restrict this to only positive y values because I know that the y value here is positive. So we're choosing that branch of the square root, so the positive part, not the negative part. Also, just a note, and I don't necessarily have to restrict this because the function itself kind of restricts its own domain, but I'm also going to write here x cubed plus 3 is greater than 0, greater than or equal to 0, just because we can't take the square root of a negative number. We don't even need to solve that. The big part here is knowing that we should restrict it to just the positive y values because y is positive here, and we can't use both branches of the square root in our solution. So this is our particular solution with an appropriate restriction on that. So here we'll separate variables. This one's pretty easy as far as separating variables go. We're just going to multiply by dx, and then take the antiderivative on both sides. So we get y equals secant of x plus c. This already has y by itself, so we'll plug in our initial condition. So pi, I'm going to do this off to the side over here. Pi over 4 is equal to the secant of 2 square root of 2 plus c. So remember, secant is 1 over cosine. So I plugged those in for the wrong thing. Sorry about that. 2 square root of 2 here, pi over 4 here. So cosine of pi over 4 is 1 over square root of 2. So secant over pi over 4 is square root of 2 over 1. So this is square root of 2. And so that means that c is going to equal square root of 2 by subtracting square root of 2 on both sides. So plugging that back in over here, we get y equals secant of x plus square root of 2. I do want to point out here, we do need to restrict the domain this time. Let me get rid of that box. This time because secant, our solution here, has discontinuities anywhere that cosine is equal to 0. So it's going to have a discontinuity of pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2. And so if we have discontinuities every pi over 2, actually it's every pi starting at pi over 2, and the initial condition is pi over 4, which is right here, then the only part of our solution that is valid is the part between negative pi over 2 and pi over 2. So we're going to say that pi over 2 is less than x, negative pi over 2 is less than x, is less than pi over 2. So again, we're restricting here for just one continuous branch of our solution. And then we have vertical asymptotes on the secant function, and our solution cannot jump over a discontinuity. It is not valid there because we don't know that initial condition really holds in another branch of it. This one, when we separate variables, remember f prime is the same thing as dy dx. So we're going to get y times dy equals negative x times dx. Take the antiderivative on both sides. Put that negative out front. So we get y squared over 2 is equal to negative x squared over 2 plus c. I'm going to go ahead and put the initial condition in at this point. We could multiply by 2 and make things a little bit easier on us, but I'm not going to do that. So we got negative 4 squared over 2 equals the opposite of 3 squared over 2 plus c. So that's going to give us 8 plus 9 halves equals c. And so we're going to have 25 halves equals c. And we get y squared over 2 equals negative x squared over 2 plus 25 halves. Solving for y, I'm going to multiply everything by 2. I am going to take the square root, and we get y equals positive or negative square root of, I'm going to write it as 25 minus x squared, or negative x squared plus 25. Doesn't really matter. Here, the domain itself is restricted by the square root. So the radicand, the inside of the square root, that has to be positive or 0. So that means that x has to be between negative 5 and positive 5. But that's not the interesting thing here. What we need to take care of is actually the y value. So again, when we have this positive or negative solution, the y value for our initial condition is negative, which means that we're actually going to use the negative branch. So we just want the negative, not the positive, because our derivative here, and I didn't really mention this last time, our derivative here is undefined when y equals 0, so we can't jump over that undefined part of the derivative. So this is our particular solution. We can include this if we want, but that's implicit in the equation itself because the radicand has to be positive or 0. But we do need to restrict it to just negative y values. That's the only place where this initial condition gives us a valid solution. Okay, separate variables. 3y squared dy equals sine of x dx. Take the antiderivative of both sides. Y cubed is equal to negative cosine of x plus c. I'm going to go ahead and plug in my initial condition here. So we get 8 cubed is equal to negative cosine of 0 plus c. 8 cubed is 512 equals negative 1 plus c, and c equals 513. So we will plug that back in. And take the cube root to get rid of the cube. Keep in mind that the cube root, being an odd root, can be positive or negative and can handle positives or negatives. So we don't really need to worry about restrictions here because we don't get any discontinuities, whether the inside of that is positive or negative. The inside is actually always positive because cosine is somewhere between -1 and +1, meaning that the entire inside of that radical is somewhere between 512 and 514. So really no problems there. So no restrictions we need to make, no problems with discontinuity with cosine, so we're good on that one. All right, last example. Let's separate variables. If you remember, I factored out a square root of y and then divided both sides by the square root of y. So that's where the y to the -1/2 comes from. Take the antiderivative on both sides. So 2y to the +1/2, or 2 square root of y, is equal to x squared plus x plus c. So plugging in our initial condition, we're going to have 2 square root of 4 is equal to 1 squared plus 1 plus c. So we got 4 equals 2 plus c, c equals 2. So putting that back in, we get 2 square root of y equals x squared plus x plus 2. Divide everything by 2 and square, and we get y equals x squared over 2 plus x over 2 plus 1 quantity squared. Now we need to consider if we're going to have any domain or range issues. The y values here and here have to be positive, but it turns out that squaring this side is going to give us something that's positive, or 0, which is okay. We can plug any x value in here and we're going to get a solution. We don't have any discontinuities, so no issues here. That's our answer.